drawing organic compounds and isomers. There are three ways to draw organic compounds. The first way, the Lewis structure, is how you learn how to draw compounds showing all the bonds and atoms back in general chemistry. So when you do that with ethanolamine, you see all three bonds to nitrogen, the four bonds to carbon, and the two bonds to oxygen. And optionally, you can put the lone pair on the nitrogen and the two lone pairs on O. Now, the bond line or skeletal structure is the most important way to draw organic compounds. It's going to mean that you're going to spend a lot less time drawing all of those CH bonds, and you'll still be able to figure out what's going on for the purposes of predicting reaction chemistry. So here we show all the bonds except CH bonds. Okay, CH bonds are just going to disappear. We don't show C's or H's connected to C's, but we do show H's connected to other atoms. So again, with ethanolamine, we see the NH bonds, but the carbons are no longer shown. They're simply the intersection of bond lines. And the H's attached to C and the bonds to those between C and H, they all disappear. You can also take the NH bonds and the OH bonds and condense them. So instead of writing N bonded to H, you just write H to N. And instead of writing O bonded to H, just write OH. So now that's our lead into the whole idea of condensed formula. With a condensed formula, you have the ability to figure out connectivity. If you look at a molecular formula, it looks like a molecular formula, from left to right. And we read the connectivity of the atoms that way. So the leftmost atom is connected to the next atom to the right, and we make that atom as happy as possible, giving it as many bonds as it needs, as we can possibly give it at least, before we go to the following atom to the right. And we keep doing that until we're done and we've connected everything together. The reason that condensed formulas are even done today is that back in the day there weren't anything but typewriters, so people would have to type structures. They didn't have chemical drawing programs, so they would type across a line, as in the case of ethanolamine, two H's connected to N. They use a subscript for the two H's, right? So H2N. Then there are two CH2s in a row, so in parentheses CH2, and then subscript 2. And that last carbon is connected to an O, which is connected to an H, so OH. So reading from left to right, you see the connectivity of the atoms in ethanolamine. Sounds great, except that there are a lot of limitations. Condensed formulas are pretty much useless for drawing rings, except for one ring, which is C6H5. That always means benzene, and you can see in the example in the bottom right, you have a ring in red, that's C6H5, that's benzene. So that is also connected to, in this structure, as CH2, which is then connected to a Cl. So as the condensed formula, we'd write C6H5 for benzene, which is then connected to CH2, Cl. Here are some examples of three different ways in which you can draw organic compounds. So with Lewis structures, you're going to show all the bonds. Bond line or skeletal structures, you're going to get rid of the CH bonds and the H's attached to C's. The C's will only be at the ends or intersection of bond lines, but you don't actually draw the letter C. You assume that they're there. And with condensed formulas, you read the connectivity of the atoms from left to right. So if you look at the top compound, we have all the bonds are drawn out, except for the bond between O and H, but that's just an optional thing. You can do that at any time. With the bond line or skeletal structure, notice all the H's attached to C's are gone, and the bonds between C and H are gone. We still see the chlorine, and we still see the oxygen attached to hydrogen, and we still see the double bond to O, because those are not CH bonds. The condensed formula, you read from left to right, so C is attached to three H's, which is attached to a carbon, and there are two of these, so we have a subscript 2. That carbon is attached to an H. That leaves one more bond to attach to the next C. which is attached to an H, which is attached to a Cl, and that carbon is also attached to a C, and that C is double bonded to O, and then that C is also connected to an O, which is connected to an H. Now, in the second line, we have a molecule that has trans geometry. That is, there's a double bond, which is rigid, and there are two identical groups. These, in this case, these are hydrogens, which are diagonally across from each other, which also makes the other two groups, which are CH3 and CH2NH2, makes those two groups diagonally across from each other. And that trans geometry can also be represented not only by a Lewis structure, where everything is drawn, and that would be kind of a pain in the neck to do, but also by a bond line or skeletal structure, which is a lot easier to draw. And in this case, I'm showing you how the NH2 can either be condensed, or you can draw out those NH bonds. Again, that's your choice. In the condensed formula, we can't do anything with that, because you can't describe with a condensed formula that the molecule is trans. You can't tell that from the condensed formula, so it's useless. With cis geometry, we now have the two H's, the identical groups, on the same side of the double bond, and we can draw that as a skeletal structure. You can clearly see that cis geometry from there, and again, this is useless in the form of a condensed formula, so you can only do cis and trans geometry with Lewis structures or bond line structures. Here are some examples of Lewis structures and their corresponding bond line or skeletal structures, and condensed formulas if possible. So in the top case, we have an OH connected to a CH2, and then another CH2, C double bond O, NH2. So if you take away the CH's, then you end up with the skeletal structure, and the C's just become the intersection of the bonds. So you don't see any actual letter C's present. But the HO and the NH2 are still shown, and you can either condense that, or you can show the actual bonds between H and O and N and H. The condensed formula is reading from left to right, so you have HO connected to C, which has two H's on it. That's connected to the next C, which has two H's on it, and since there are two of those in a row, you just put CH2 in parentheses, subscript 2. Now that last carbon's connected to another C, which is double bonded to O. Remember, the O gets as many bonds as it can get from the C. And now that C still has one more bond, which it uses to connect to N. So N is next, and that N is connected to two H's. Now in the middle example, we have what is known as cis geometry on a ring. That is, you have two groups which are both coming towards you or both going away from you. These two groups, the bromine and the CH3, are on wedge bonds, so they're both coming towards you. That's cis. They're pointing to the same side of the ring. If you look at the skeletal structure for that, take away all the CH's, make all the carbons just the intersection of bond lines, and the CH3 is at the end of a bond, that disappears too, and you get the skeletal structure. And you can still see that it's cis. You just have to spend all that time drawing all those C's and H's. And the bottom structure, you have the trans geometry. The two groups, the bromine and the CH3, are now pointing in opposite directions. The bromine is a wedge, okay, so that's a bond coming towards you, and the carbon to CH3 bond is on a dash, so that's a carbon group going away from you. And the much simpler skeletal structure, again, shows that wedge and dash relationship, so you can still tell it's trans. Now note, with the condensed formulas, you cannot draw either the ring or represent cis and trans, so condensed formulas are useless for this type of structure. You can't use them. Practice problem 1. Convert each Lewis structure into a bond line or skeletal structure. At this point, you will want to pause the video so you can work on these problems. Answers to practice problem 1. In part A, I've made all of the CH bonds red, so those H's and their bonds to C are all going to disappear. The The C's, of course, are going to become either the end of a bond line or the intersection of bonds. And so you see that that now becomes the two possible representations for a skeletal or bond line structure. The OH can either be drawn out or you can condense it into just OH. In part B, again, I get rid of all of the CH's and the C's become the intersection of the bond lines, and I have the two possible bond line or skeletal structures represented. S bonded to H can be condensed if you like, and it's a trans geometry. In C, I have a ring. I get rid of all my CH bonds, and I end up with still that square, but the NH2 and the CH3 are now simply wedges. One wedge has an NH2 on it, either with the bonds shown completely or just abbreviated NH2, and the wedge that had the CH3 is just a wedge. There's nothing at the end because the carbon disappeared, and so did the H's. In D, I have initially a CH3, and then a CH2, and finally a CH. These are where all of my CH bonds are. Those all go away. There's one other carbon, and that is in between a C and an O, double bonds to both sides. That makes it a little difficult to draw. You have to kind of slip the double bonds apart from each other. Some places they actually just put a dot, a heavy black dot in between. But either way, now you can see that there's a break in between that means that there's a carbon there that you have to think about, rather than simply trying to draw a very, very long double bond, which wouldn't tell you anything about having a carbon in between. So you really have to show that break as seen in the skeletal structure, so that you know there's a carbon in between, two double bonds to that carbon, or put a heavy black dot there. Practice problem 2. Convert the following condensed formula into a Lewis structure and a bond line or skeletal structure. Remember, now what you're going to do is you're going to read from left to right. So, for example, you've got a carbon atom on the left. It's bonded to hydrogens on the right. So there are 3 of them. So you want to make 3 bonds between carbon and hydrogen. And then it's in parentheses 3, which means that all 3 of those groups are connected to the next atom, and so forth. Answers to practice problem 2. Okay, we start off with the carbon connected to 3 hydrogens, giving us our CH3. There are 3 CH3s. They're all connected to a carbon. And then that carbon still has one more bond, which it uses to connect to the next carbon. And that carbon has a double bond to oxygen. That satisfies the oxygen's bond requirements. Now, the carbon that's double bonded to oxygen still has one bond left. It makes that bond to the next atom, which is nitrogen, and nitrogen needing 3 bonds creates a 1 bond each to the hydrogens, giving our final Lewis structure. Now, converting that Lewis structure into a bond line or skeletal structure, we get rid of all the CH's. The carbons are just going to be the ends and intersections of bond lines, and ta-da, we have our final bond line or skeletal structure. Remember that the NH's can be either explicitly shown or just abbreviated as NH2. A single molecular formula can represent a wide array of different compounds. It just depends on how you arrange the atoms in space. These are isomers, and we're going to look at 2 classes of isomers. The constitutional isomers have the same molecular formula, but different connectivity of atoms, meaning the atoms are not connected to each other in the same way. You've moved atoms around in the structure, so not in the same place. If atoms are in a ring, that's called cyclic. If they're not in a ring, it's called acyclic. Okay, these would be constitutional isomers of each other. So if you look at C3H5Cl, the molecular formula, here are 3 ways that could be represented. These are not the only three ways, these are just 3 possibilities. You could have the chlorine at the end of a carbon chain, and then there's a carbon-carbon double bond. But you could also move that chlorine from the end of that carbon chain to the middle. That changes the position of the chlorine atom, so now these are constitutional isomers. The last case is a ring. So we've gone from the acyclic case, or cases, where they were not rings, to our cyclic case, where the chlorine is attached to a triangle. The carbons are all connected together in a ring. There's no carbon-carbon double bond, so very different constitutionally. Diastereomers have the same molecular formula, but they also have the same connectivity of atoms. So you wouldn't go from acyclic to cyclic. You wouldn't change the positions of the atoms, but you can change the distances between the atoms. And here's an example. Again, with C3H5Cl, you have a situation in the first case where the CH bonds in red are diagonally across from each other on the double bond. They're rigidly placed because you can't twist around that carbon-carbon double bond without breaking the pi bond. So that forces them to be permanently diagonally across from each other, and that's called trans. If the two hydrogens are on the same side of the double bond, that's called cis. The distances between the CHs are smaller in the cis case than in the trans case, so therefore they are diastereomers. There are different distances between the atoms. Okay, let's look at some examples of isomers with the molecular formula C6H11Br. Okay, if you look at A and B, okay, you have the bromine and the CH3 group, which are both wedges, so those are bonds that are both coming towards you. That would be considered cis. In B, they're trans, so the distances are different, but they're both attached in the same places, and they're still both on a five-sided ring. So these are diastereomers of each other. They only differ by the distances between the groups. C through F, okay, would be constitutional isomers of A and B, because you have moved the positions of the carbon atoms in the cases of C, D, and E, and in the case of F, you've actually changed the size of the ring. If you look at C, C is a constitutional isomer of all the other isomers, because compared to C, everything is completely changed, either the size of the ring or the position of the carbon atom. So the CH3 has been moved around quite a bit. In every other case, D and E are diastereomers of each other. The bromine and CH3 group are on the same side, cis in D, but they're trans in E. They are all constitutional isomers of A, B, C, and F, again because we've moved the position of the CH3, and in the case of F, we've expanded the ring. F, the only six-sided ring represented here among the isomers, is thus a constitutional isomer of all the other isomers shown here. Practice problem 3. Classify each pair of isomers as constitutional isomers, diastereomers, or identical. Now, compounds can be identical if you just flip the molecule around, rotate it about, or twist around a single bond so that it looks different, but remember, as long as the molecule is not a ring, you can just rotate freely around the single bonds. Answers to practice problem 3. So in part A, we have a trans versus cis situation. The CH bonds in trans are diagonally across and cis are on the same side. So the distances between the atoms are different, thus these are diastereomers. In B, all you did was rotate the OH group into a different position through simple C-C bond rotation that flips the OH up. Thus, these two compounds are identical. In C, the double bond is moved from inside the ring to outside the ring. That changes the position of the double bond, thus also atoms that are attached to the double bond. And that changes the constitution of the molecule. So these are constitutional isomers. In D, we have another trans-cis situation, but this time we're talking about wedges and dashes on a ring. So you have a chlorine and an OH group pointing in opposite directions. In the first case, that's trans. And now they're both pointing away from us. In the second case, that's cis. So these are diastereomers because the OH and the Cl bond have different distances from each other. In the trans case, they're further apart than in the cis case. Considering the biological significance of isomerism, first have to recognize that these isomers we've been talking about, the constitutional and diastereomers, all have different chemical and physical properties, which means that they are all going to have different reactivity, they're all going to have different boiling points, melting points, solubilities in water, etc. They'll also have different biological effects. So if you look at the top examples, these three compounds all have the same molecular formula. They are isomers of each other. The first case, we have an OH attached to O. We have an OO bond. It's a particularly unstable bond. It makes this compound highly flammable and explosive. If we simply remove that OH from being attached to O and place it on a carbon instead, specifically a carbon which is 2 carbons away from the one with C double bond O, now we have food. This is something which your body can turn into energy. If we move the OH one step further, all the way at the end of the carbon chain, now we have something which is horrible. Okay, we have GHB, an illegal drug used to incapacitate people, the so-called date rape drug. These three compounds are simply isomers of each other. In fact, they're constitutional isomers, and they're completely different in their biological effects and their chemical and physical properties. Now, if you look at the bottom two cases, we have E-triprolidine, which is commonly known as Actifed. It's an antihistamine in cold remedies, and it is 1,000 times more effective than Z-triprolidine. Now, what distinguishes these two? If you look very carefully, the connectivities are the same in both the E and Z isomers, but the distances between the atoms are different. The nitrogen in the 5-sided ring is closer to that benzene ring in E-triprolidine than it is in Z-triprolidine. There it's diagonally across from that benzene ring. So that makes them diastereomers, and these two diastereomers have wildly different biological effects, so that one is a drug and the other one is useless. How do you make correct structures from a molecular formula? In order to do that, you have to do more than simply take a molecular formula and then randomly start drawing things, because you will always make mistakes that way. You need to know if pi bonds or rings are essential in the formula, that they're needed in the formula. If they aren't, then we say that the molecule is saturated. There are no pi bonds or rings present. If they're needed, we say that there is unsaturation. Each pi bond or ring equals 1 degree of unsaturation, or 1 DOU. So when you calculate the DOU, you know you have to draw a molecule with that many pi bonds and or rings. So DOU equals the number of carbons in the formula plus 1 minus a half, or 0.5, times parentheses the number of hydrogens minus the number of nitrogens plus the number of halogens end parentheses. And halogens are fluorine, chlorine, bromine, or iodine. So let's see. In the case of C2H3N, we have DOU equals 2 carbons plus 1 minus 0.5 times parentheses 3 hydrogens minus 1 nitrogen end parentheses. So that's 3 minus a half of 2, which is 1, so 3 minus 1, or 2 DOU, 2 degrees of unsaturation. 2 degrees of unsaturation means there could be 2 pi bonds, or if there are enough atoms that could make rings, 2 rings, or 1 ring and a 1 pi bond. So let's see some examples here for C2H3N. You could have 3 hydrogens connected to a carbon, and then that's connected to a C triple bond N. if you were to draw the structure, you start with the C triple bond N, which has the 2 pi bonds, and then all the rest have to be single bonds. You could also have 2 double bonds, which would be 2 pi bonds, one carbon-carbon double bond and the other carbon-nitrogen double bond. Now remember, in the skeletal structure or bond line structure, since these are 2 fused double bonds, you have to show them kind of slid a little bit past each other, so there's a little bit of a broken juncture between the 2 double bonds, or you have to show a heavy dot where the carbon would be. The ring example would be a ring with a pi bond. So you notice there it is, a carbon-carbon double bond, and the nitrogen is creating a ring with the other carbons, and that would give you 2 degrees of unsaturation, 1 ring and 1 pi bond. Practice problem 4. For each molecular formula, draw 2 isomers as bond line or skeletal structures, 1 acyclic, which is not a ring, and 1 cyclic, at least 1 ring. Don't forget, you should figure out the degrees of unsaturation using the DOU formula and put in the pi bonds and or rings first before you figure out the rest of the structure. Okay, so because the rest of the structure is going to be simply single bonds. So figure out where your pi bonds are, draw that in, draw carbon-carbon double bonds, carbon-oxygen double bonds, whatever you want to do. Draw a ring if you want, but make sure you establish those DOUs first before you draw in the rest of the atoms in the molecule. That's the only way you're going to figure this out correctly. And I would recommend drawing a Lewis structure and then converting that into your bond line or skeletal structure, so you can keep track of all your atoms. Answers to practice problem 4. Well, in part A, the DOU is equal to 1, and there are several different possible acyclic structures. I'm giving you some examples here that it's not exhaustive. You could have drawn something different. And in each case, there's 1 pi bond, and I've used in the top example C double bond O for our pi bond. In the middle example, I have C double bond C. The Cl and OH are in different positions, and in the bottom structures it's still C double bond C, but now in one case I have an OH, and in the right case I have O to Cl. These are just 6 of several possible acyclic structures. There's actually only 1 cyclic structure possible, and that's the one shown here, a 3-sided ring with an oxygen, and there's a chlorine coming off of the carbon. Remember, chlorine can only make 1 bond, so the only atoms that can make a ring would be the 2 carbons and the O. That can only make 1 ring. If you look at part B, the DOU is 3, so we have a lot of possibilities here. You can have 3 pi bonds. So in our top example, I use C double bond O and C triple bond C. That would give it a 3 pi bonds. The triple bond has 2 pi bonds, and there's 1 pi bond for C double bond O. And in the middle example, I have a sequence of 3 fused pi bonds, C double bond N, C double bond C, and C double bond O. And the bottom structure, I have another case of a triple bond, this time between C and N, so that's 2 pi bonds, and our last pi bond between C and O. Now, some possible cyclic structures. I've decided to give you an example of the case of 1 ring and 2 pi bonds, 2 rings and 1 pi bond, and 3 rings. So in the top case, we have 1 ring, a 4-sided ring, with 2 pi bonds, carbon-carbon double bond and carbon-oxygen double bond. In the middle case, we have 2 rings. They're twisted. Notice how one of the rings is in the plane and the other one has a wedge and a dash. And there's a double bond. So there's 2 rings, 2 3-sided rings, and 1 pi bond. And in the final case, at the bottom, it's a little bit hard to visualize. You have a very 3-dimensional structure. You have 3 triangles fused together. Those are the 3 rings. One is bridged with an oxygen, one is bridged with a nitrogen, and the other is bridged with a carbon. They're all fused together to give us 3 degrees of unsaturation.